Hello everyone. Here in this video, we would like to show an example for the oscillatory motion, right? So, what is an oscillatory motion? As I told you earlier, it's a to and fro motion about a fixed point. Many times, that fixed point is called as a mean position or an equilibrium position. So, we are taking an example of uniform circular motion, but uniform circular motion is not a oscillatory motion. Vertical projection of uniform circular motion. I will explain what do you mean by vertical projection is in the coming 2-3 minutes. So first let me consider a uniform circular motion. So let us consider a fixed point. If a body is revolving around this fixed point like this in a circular path with a constant speed, direction changes, therefore velocity changes. But if the speed is constant, then that is called as a uniform circular motion. So consider a body who is revolving in a circular path like this. This is the radius of that circular motion. Then that need to be a perfect circle. Well, shall I draw a perfect circle for you? Yeah, let me try. Just give me a second. Yeah. I'll just eliminate this. Just to draw a perfect circle for all of you. Just to make it better, look better. No, just a second. Yeah. So this is a perfect circle. So let us consider a body moving in this circular path about this point is the radius of that circular path. This is the body. This body is, if you consider this as an origin, say this is the positive x-axis, this is the negative x-axis, this is the positive y-axis, this is the negative y-axis. This body is rotating in this circular path this way. So in an anti-clockwise direction. It could be anything, just I have taken an anti-clockwise direction. Now I want to draw a vertical projection for every position of the body onto the y-axis, right? So onto the y-axis. Of course, I can draw a vertical projection onto the x-axis also, but first I am drawing onto the y-axis in the first case. So what happens in that case? See, when the body is at x, you draw a vertical projection, draw a line onto the y-axis. Where is it? It is at a point O. So I'll draw a line, a kind of a position. And I will also tell you where is its vertical projection is. So when the body is at x, its vertical projection comes to a point O. Now you slowly rotate this way. You come to a particular point. How do you draw a vertical projection? Like this. This is your vertical projection. Now you come to the point Y. That itself is a vertical projection because point Y is on y-axis. So when your position is Y, its vertical projection is also at Y. Now we'll slowly come to somewhere here. Here the vertical projection means you have to draw a line onto the y-axis somewhere here. So you have noticed it has started from origin. It has gone up to the Y and now it started coming down. And when the body is at x dash, its vertical projection is back to the origin. So when the body is at x dash, its vertical projection is at O. So you came up to here, you are coming this way. Here is the vertical projection here on y-axis. So it's again started coming down. So when the body is at a position y dash, negative y-axis, Vertical projection is also on y dash because y dash is on y-axis itself. So if you repeat your motion, that means you go to this position, its vertical projection comes back to this. If you go back to x, its vertical projection also goes back to O. So what we have noticed is, if you say you have started moving from y, you have gone back to y, from x to y, then vertical projection is also at y itself. So you just consider that you have started from the position y, so that it will be more convenient to understand the oscillatory motion. Yeah. So you have started from a position y. Oh shit. Yeah. Let's give a second. Yeah. You have started from a position y. Its vertical projection is also y. I will draw the diagram again for you just to explain what do I mean by that, right? So I'm just drawing a circle. Your body is here, at y. Its vertical projection is also at y. You are slowly coming here. When you come to say x dash, its vertical projection comes to origin. That's what I have written here. When you come to y dash, vertical projection is also at y dash because that's on y axis. When you come to x this way, vertical projection comes back to origin. When you go back to y, vertical projection is at y itself. So when you complete one rotation, look at this. This is one rotation. You have started from here, y. You have completed one rotation this way, y. This is y. Then we came to x dash. Then you go to y dash. Then you go to x, and then you go to y. That's one rotation of a uniform circular motion. See how the vertical projection has moved. Vertical projection has moved from y, then come to O, then come to y dash, then again to O, then again to y. See, this way. So what is the movement of the vertical projection? If you notice little more carefully, I want you to notice that more carefully. Yeah. Vertical projection has started at y, gone to origin, gone to y dash here, and then back to origin, back to y. See this. See how the vertical projection has moved with respect to circular motion. Vertical projection has moved this way. Which way? From y to y dash, back to O, back to y. Have you not noticed that this is an oscillatory motion coming down, going up about a fixed point O? Bottom point is y dash, upper point is O. That's what you mean by a oscillatory motion. So the first thing that I have proved here is I have proved one thing for you. What is that I have proved here is vertical projection of uniform circular motion is oscillatory motion. Be careful to understand that I have not yet proved this as a simple harmonic motion. I have only proved that this is a oscillatory motion. So to prove that it is a simple harmonic motion, I have to prove other conditions, that acceleration is directly proportional to displacement and they are in opposite direction. That's the third condition. For that, I have to derive an expression for displacement, velocity, and acceleration. We will do that over the course of time.